Hello, everyone. In the previous video, we stopped with talking about how when you solve the cost minimization problem, the amount of K and L that happen to be the low-cost combination of inputs that you need in order to produce a fixed level of output, those demands for the inputs are actually called contingent demand. And that's because they're contingent on the level of output that is being produced. And that's why we indicate these demands with a superscript C. We should just remember that any input that is being demanded will generally depend on how much ever output is required to be produced. So all of these input demand functions are called derived demand functions. Now, in this chapter, we're focusing on minimizing costs subject to a certain output constraint. And so the solution to that problem gives us contingent demand functions. Now, on to our next concept. Now, in this manner, we can actually identify the firm's cost minimizing combination of L and K for any given level of output. So if it was, if you look at the chart here, if the level of output is Q1, cost minimization happens at that point. If the level of output goes up to Q2, then the low cost combination of K and L is given by this tangency between the isoquant and the budget line. For higher levels of output, say Q3, the tangency happens at a different point. Now, if we were to assume that the input prices remain the same, okay, if W and V don't change, then that means all of our isocost lines will have the same slope. Their slope isn't going to change. Now, under that scenario, we can actually trace the low-cost combination of inputs for different levels of output. And if we trace just the locus of all of those optimal solutions, so if I were to trace a line from the origin and go through all of these optimal points, what I get is called the firm's expansion path. Keeping input prices fixed, it tells you how the firm's input use expands as its output production increases. So that's what an expansion path is. Now you can see in this chart, in this figure here, that the expansion path is not necessarily linear, and that is perfectly fine. There are certain inputs that we may use a lot faster than a few other inputs as we are increasing the output level. Now, when you have homothetic production functions, expansion path there will be a straight line. So if you remember, whenever you have homothetic functions, every successive isoquant is just a radial expansion of another one. So they're pretty identical. So if you just draw a line from the origin that's like cuts through all of these isoquants, the point wherever that ray is cutting an isoquant, if you measure the MRT as there, it'll be the same at every single isoquant. So if our, if a particular point of tangency happens, say here, okay, for homothetic production functions, if the output were to increase to a different level, and given that the input prices haven't changed, my point of tangency will happen at a slightly, at a higher level on the northeast. But because these are homothetic production functions, the slope at this particular point A will be exactly equal to the slope at point B, so on and so forth. So if I draw a line from the origin, it will be a straight line. And that line is nothing but my expansion path, which is just tracing the locus of my cost minimizing combinations as my output levels are expanding. Now, we've looked at cases where the expansion path is an upward sloping line. Again, that need not always be the case. So when you have inputs which are, say, inferior, you may prefer to reduce the use of such inputs as you expand your level of production. In that case, as you produce more and more output, you might just tone down or reduce your use of certain inputs. So in this case, when we're using labor and capital to produce something, our expansion path takes a turn after a certain level of output. So when we go from Q3 to Q4, or even actually from Q2 to Q3, we use more of capital, but less of labor. You see that, here there's more labor that is being used, then a tinier reduction in the amount of labor. And when we climb up to Q4, the amount of labor that is used is even lesser. So labor is an inferior input here. So that's in such cases, you can see that your expansion path can actually curve in a different direction. So for example, if you're a building contractor, if you're initially using, say, shovels, according to the graph, labor is an inferior input, but you could think of other scenarios where different types of tools are being used to produce something. Initially shovels may be great, but as you come up with better inputs in place of shovels, then shovels start becoming inferior, and you're just going to start using these huge backhoes to get the job done. So that's about firms' expansion paths. Yeah. And now we close this video with just a couple of quick cost minimization examples, just to walk you through the calculus of how this is done. So we'll look at a case of a Cobb-Douglas function and the CES reduction function. So we have a general Cobb-Douglas function here of the form k power alpha L power beta. And our goal is to minimize costs subject to some level of output, Q0. So our objective function will be costs equals WL plus VK. So a Lagrangian will be to optimize the objective function subject to our some production constraint. So we go ahead and write down our first order conditions with respect to L and then with respect to K. And I'll let you do the calculus on your own. I'm sure all of you know how to solve this. And then the third first order condition with respect to lambda. Oftentimes our interest will generally be in these first two conditions. And when you divide the first order condition 1 by the second first order condition, we get this particular result that W over V is equal to beta by alpha times K over L. And this is actually nothing but the rate of technical substitution of a Cobb-Douglas function. And so this equality of the price, the price ratio equaling the MRTS, that holds perfectly in the Cobb-Douglas case. And you will also notice that the RTS is now just a function of K by L ratio. So whenever your rate of technical substitution depends only on the K by L ratio, but not the absolute amounts, then you have homothetic functions. With homothetic production functions, your expansion paths will be straight lines. Then the next example is one of a CES production function. So that's given to us right there. We're just going to write down a Lagrangian in the same way as before. Our goal is to minimize costs subject to our output constraint. And if we were to take the first order conditions, note that all the Greek symbols that you see here, the rho and the gamma, they're all parameters here. So our goal is to just find out the cost minimizing values of L and K. So we take the derivative with respect to L, we then take the derivative with respect to K, and then with respect to lambda, and focusing our attention on the first two derivatives. If we actually divide one first order condition by the other, we get a particular condition that my W by V should equal K by L raised to the power 1 minus rho. And in CES functions, sigma is just given by 1 over 1 minus rho. That's just your elasticity of substitution. So if I just make some rearrangements numerically, I end up getting the result that the capital labor ratio depends on a particular ratio of the prices raised to sigma. So this function is also homothetic. And just by varying the values of sigma, we can try and understand by how much capital labor ratio can change when you change the price of inputs. That is just more for intellectual exploration. So with that, I bring this video to a close. I'll see you in the next one.